So in this video, we're going to talk about lines and planes in space. We'll start a discussion here with parametric equations of lines. And in algebra, you've probably been told many times that for an equation of a line, you need two things. You need a point and you need a slope. Well, for parametric equations of lines, when we're dealing with vectors, we're going to need two things again. One of them is going to be a point, and the other one is going to be a direction vector. So you can kind of think of it as the slope component of the line, but now again, dealing with vectors. So we'll start with a picture here where we have the XYZ space, and let's say that we have a line cutting through it, and the point on our line that we're going to use will be P naught, which would be a point X naught, Y naught, and Z naught. Then we'll need a direction vector. The direction vector is going to be in standard position, so I'm going to write it in component form as vector A, B, and C, and that direction vector is going to be parallel the line. So the direction vector V was A, B, C, and the point P naught was X naught, Y naught, and Z naught. So to get this all put together, I'm going to select another point on the line. Maybe I'll just say P, which is X, Y, and Z. The reason I've selected that is because now I'm able to take 2 points on a line and create a vector. So if you'll remember, the vector P naught P needs to equal TV. Now where did that come from? Well, we know that this vector, when put in standard position, using the correct notation and creating a vector out of those 2 points, is going to equal a scalar multiple of vector V. And we know that because they're parallel. And so when two vectors are parallel, they're scalar multiples of each other. The t that you're looking at here, this guy, that t, that's the parameter. So vector P naught P is going to be our x minus x naught, y minus y naught, and z minus z naught from an earlier video on how to construct a vector out of 2 points. And this is going to equal t vector A, B, C. So I substituted vector V in there. So now I'll go ahead and distribute the t. So x minus x naught, y minus y naught, z minus z naught equals, we've got a TA, TB, and TC. And now I've got two vectors equaling each other, therefore corresponding components must be the same. So x minus x naught needs to equal AT, y minus y naught needs to equal BT, and z minus z naught equals CT. If I solve each of these for x, y, and z, I'm going to end up with x equaling x naught plus AT, y would equal y naught plus BT, z would equal z naught plus CT. So these are in fact the parametric equations of a line, specifically the line with point x naught, y naught, z naught, and direction vector ABC. It's very important to recognize when looking at these, you can directly pick out the point and the direction vector without having to do any work. The coefficients on the parameter, the A, the B, the C, those are the components of the direction vector. The coefficients out here all by themselves, the x naught, y naught, and z naught, these constants, these are going to be coordinates for the point that runs through the line. So assuming you have a point and a direction vector, you can easily construct or even deconstruct the line depending on the context. All right, so in the first example we look at, we're going to find the equations, the parametric equations of the line that passes through the point and parallel to this line right here. And so remember, if we're going to come up with the parametric equations of a line, we're going to need two things. We're going to need a point and we're going to need a direction vector. So we've got our point, now we just need our direction vector. Well, if we think about it, this is a line and it has its own direction vector. The direction vector for the line given is going to be the coefficients out in front of the parameter. So we've got a 3, a 1, and a -1. So those components put together give us our direction vector. So 3, 1, -1. Now, since it says parallel, we can use the exact same vector. So the direction won't change. It doesn't matter the magnitude. We don't care about that. We just care about the direction. So as we put this together then, x is going to be the x-coordinate of the point, 2, and then plus 3t, the 3 coming from the x component of the direction vector. The y would be put together pretty similarly, -1 plus t, and then z would be the 5 minus t. Again, the -1, the -1, the 5, the 5. So here's our ordered pair or ordered triple, excuse me, in the point that runs through our line, and then the components of the direction vector, 3, 1, -1. All right, so in this example, we're going to take a look at 2 different lines and determine if they're parallel, intersecting, or skew. Skew means not parallel and they don't intersect. So skew is not parallel, but they still don't intersect. So we'll take a look here at the problem given, and you can see that we are given 2 lines, just as kind of something that I like to personally do. We want to keep in mind that we're dealing with 2 separate lines, and so what I'll do a lot is actually add subscripts to the t's in each of the lines. So for example, I might call this t sub 1, 1, 1, and then t sub 2, 2, 2, because those aren't necessarily the same t's, and we want to keep track of things, but that's just personal preference. So first thing I'm going to do is determine if they're parallel. And so in determining if they're parallel, I'm going to pull out their direction vectors, and in this first one we'd have a 4, 1, -2. So 4, 1, and -2 for that direction vector. And then for the second one, we would have a 6, -3, and 8 for that one. Now, looking at these, I can say that they are not parallel. So how can I say that? Oh, I can say that because these 2 vectors are not scalar multiples of one another. Since they're not scalar multiples, the lines cannot be parallel. So to figure out then if they're intersecting or skew, we'd want to go ahead and essentially determine if they're intersecting. If they're not, then the conclusion would be skew. So to determine if something is intersecting, we'll do what we do a lot of times. We start setting things equal to one another. So what I'll do, and this certainly can be done other ways, I'll take this z value and I'll set it equal to this z value. So in doing so, I'll get a -5 minus 2t1 equals a 5 plus 8t2. And so then I'll manipulate this a little bit and solve this for t1. Again, it's mostly just because I have to do something, and so I'll solve it for t1. This will give me a -5 minus 4t2. So now I'll go ahead and I'll take that, and I'm going to go ahead and substitute it in, let's just say this guy here. So my t sub 1 is going to be this, which means that my y is going to be 6 plus -5 minus 4t2. And then I'll go ahead and set it equal to this guy right here, the 2 minus 3t2. And so now that's going to allow me to go ahead and solve for t2. So I'll spare you a little bit of algebra, and we'll see that t2 is going to equal -1. If t2 equals -1, then I'm going to come back up here, and if I plug that in for t2, that's going to tell me t1 also equals -1. So then, if I take both of these values right here and plug them in up here, so t sub 1 would go there, and that would give me an x value, would go there, give me a y value, there, z, and same thing for t sub 2. Those will give me then 2 points. If assuming these 2 points are the same, then that's going to be our point of intersection. So as I plug my t1 in, that's going to give me a 7, a 5, and a -3. Same thing here, a 7, a 5, and a -3 when I plug them in which case we figure out that these 2 lines right here intersect at the point 7, 5, -3. So we determined they weren't parallel. We did find that they intersected and where. If we find out that they don't intersect, then we would say that the 2 lines are skew. Again, skew is not parallel and they don't intersect.